Hey guys, hey, welcome back. Welcome back to your most recent installment of Learning Algebra with Mr. Bauman from Mr. Bauman's Basement. Coming right back at you. Same basement, same subject, a little bit different scenery behind me, but we are getting so close. So close to the end of the school year, as crazy as it may seem, but we are, this is going to be the last official section from Chapter 10. Here in the last few weeks of the school year, we're going to be hitting a couple sections in Chapter 11, and then at that point, you guys are ready to hit the ground running when you get to high school in just a few short months. And I've tried my best, believe me, I've tried my best to get you guys prepared for that, whether we're in school building or I'm teaching you from my basement. I hope I'm feeling confident that you guys are going to feel confident when you walk into that first day of high school. So I appreciate all the hard work you've given me all year long, but especially here in the last 5 or 6 weeks. I know it hasn't been ideal, but I certainly, truly, I certainly appreciate all of the hard work, and I hope you guys are starting to see the payoff. If you haven't yet, I know you'll see that payoff when you get to high school. You guys are going to be rock solid. You're going to rock and roll when you get to high school algebra. I know it. So we are so close. It's so close I can smell it. We're almost there to the end of this algebra course. So I've got my supplies, as always. Got the whiteboard, got the marker, got the magical eraser, and of course, no good math lesson is complete without a somewhat warm cup of joe. You like this? This is a Christmas gift from Lily, actually. So here we go. One of the last sections. It is the last section that we're going to cover here in Chapter 10. 10.3. Pause the video if you need to. Operations with radicals. What does that mean? By the time this video ends, you should be able to add, subtract, multiply, and divide radical expressions. You're going to be able to add, subtract, multiply, and divide radical expressions. So I'm going to walk you through kind of the steps in order to do this. A lot of this is going to be a review. We're going to look at the distributive property. We're going to look at FOIL again. So I hope you're realizing that a lot of these topics, a lot of these standards are very progressive, that you can't do the things we're doing now unless you fully understood the things we did earlier in the school year. So that's, again, why I think you're starting to see the payoff of your hard work, and I really appreciate everything you guys have done. All right, title and objective. Let's jump right into it. If this was 7th grade, we talked a lot about like terms in 7th grade. And like terms could be added or subtracted. They can be combined together, right? So if we looked at negative 12x, this is just review from 7th grade. If we looked at negative 12x and positive 3x, first of all, are these like terms? Absolutely. They have the same variable part, right? And any two like terms could be added together. So if you had negative 12x and you added 3x, you would have negative 9x, right? That's the sum of these two like terms. In much the same way, maybe the like terms were negative 4x squared, so you could have a higher exponent than 1, and 6x squared. Those are also like terms, and they can also be subtracted. If you had negative 4x squareds and then you lost 6 more x squareds, you would have negative 10x squared. So they can be combined. That was like 7th grade, first part of 8th grade. Why do I bring that up? Today, we're not going to be looking at like terms. It's a different vocab word for today. I've got a different board already written here. In algebra, we focused a lot on like terms at the beginning of the year. Now that we're towards the end of the year, we're looking at what's called like radicals. So this is a definition, the only definition for today, like radicals. In very similar way to like terms, like radicals can be added and subtracted. That's one of the things we're going to be doing today. But what makes them like radicals? By definition, like radicals have the same radicand. Remember the radicand? That's what's underneath the square root symbol, underneath the radical symbol. All of the stuff, all of the expression underneath that symbol is called the radicand. So if you have two of them that have the same stuff underneath the radical symbol, we call them like radicals. And like radicals can be added or subtracted. That's really at the heart of what we're doing today. So if you need to pause the video, leave that up one more time. Pause the video if you need to. Let's jump right into the first example. So that's kind of the background information. Let's jump right into this. If we had -7 radical 3 plus 12 radical 3. -7 radical 3 plus 12 radical 3. I'm going to move this camera down just a bit. There we go. Now, first things first, this is one term. This is another term. Remember, terms are things that are added. This has a radical symbol, so does this. The stuff, in fact, right now it's just a number, the radicand here and the radicand here are the same, which makes these like radicals. So this one and this one, you might want to go ahead and describe in words what we're adding here. We're adding like radicals. Just like terms, like radicals can be combined. If you had -7 radical 3's and someone gave you 12 radical 3's, how many radical 3's do you have? Let me get some space here. If you had -7 radical 3's and someone gave you 12, how many would you have? That's right, you'd have +5 radical 3. It's very similar to what you're going to be doing in the very first question on your Google Doc today. Very simply adding like radicals. All right, let's move right on to, just like always, if you have questions, you're not sure how I did that, email me. I've had some of you in the last 5 or 6 weeks shoot me emails during the day. I try to check it somewhat often, every hour or so, and I try to respond as quick as I can. So if you do have a question, make sure you send me an email. Let's move into the second example. Same directions, simplify. But this time, let's look at two radicals that on the surface initially are not alike. What if I gave you 5 radical 32 minus 4 radical 18? 5 radical 32 minus 4 radical 18. Initially, you might look at this and you're like, Mr. Bauman, you can't do anything with this because this radicand is not the same as this radicand. And I would agree. Initially, it doesn't look like you can do anything with this. But using what you learned last video, just a few days ago, can this be simplified? In other words, is there a perfect square factor of 32? And the answer is yes. Go for the biggest one, because 4 definitely goes in, but there's one bigger. That's right, 16. 16 goes into this one. How about this one? Can this be simplified? Yes, because, again, there's a perfect square factor. What's the perfect square factor of 18? That's right, it's 9. So let's first simplify this, then see if we can subtract. All right? So we're going to split this first one. This is going to be 5 times, we said 16 is the perfect square factor, times radical 2. So I just simplified this first one, this first term, to this. And then I'm going to subtract 4 times, we said the perfect square factor was 9. 4 times radical 9 times radical 2. All right, let's do some simplifying. You should be able to do this one mentally. This is really 5 times 4, because that's the square root of 16. That's 20, radical 2. Then the second one is really 4 times 3. That's 12, radical 2. Oh my stars. We now have two terms that have the same radicand, so we call these like radicals. Now let's go and combine them. If you had 20 radical 2's and someone steals 12 of your radical 2's, how many radical 2's do you have left? You have 8 radical 2. And just like the previous section, the previous video, check it. If it doesn't have variables, you can certainly check this with your calculator. This is the exact answer, but if you wanted to approximate it, take out your calculator, do 8 times radical 2. I don't have a calculator down here, I keep forgetting to bring it. It's going to give you some funky decimal because 2 is not a perfect square. Now, write down that decimal, go to like the nearest 4 or 5 digits, decimal places. Now do your original problem on your calculator. 5 times radical 32. Again, you're going to get some funky decimal. Then subtract 4 radical 18. Guess what? This decimal up here should be about the same as this decimal down here. Again, just a nice way to check your work tonight, but especially next year in high school. All right, let's move along. Believe it or not, we're almost halfway there. So that's adding and subtracting. You're going to be doing both of those tonight. Let's move on to multiplication and division of radicals. So you might just kind of subtitle your notes, multiplying and dividing radicals. Like almost every video I've done here, I'm really combining 2 days worth of instruction into one video. So I'm just going to try to keep moving forward so the videos hopefully shrink in length. And let's call this example 3. Same directions, except this time instead of being adding and subtracting, let's try to do a product. Let's try to multiply some radical expressions. So let's start with radical 2 and then left parenthesis radical 6 plus radical 5. Every problem that we do here on the board is going to be very similar to every problem that you're going to be doing in your Google Docs. So please make sure you take good notes, number one. Number two, don't throw away your notes here in a couple weeks. Don't throw them in a bonfire this summer. Keep them. Use them for 9th grade algebra. And finally, if you need to re-watch this video to help you with the Google Doc today, that's why I'm doing them on YouTube, so you can re-watch it. You can go back and play back. All right, so here's our first factor. Why is it a factor? Because technically what symbol is right here? We just don't write it? That's right, it's a multiplication symbol. So that's really multiplication. And then this is a quantity. These cannot be combined because the radicands are not the same. So we're going to have to multiply radical 2 times this quantity. In order to do that, we have to use the distributive property. That's right. So let's distribute. I still draw arrows. Been doing this for 30 some odd years. And I still draw arrows ever since I was in middle school. So let's try this out. Radical 2 times radical 6. Guess what? That's just what you learned last section. We can multiply those two radicands. That's radical 12. Then we can distribute the radical 2 here. That would be radical 10. Can these two be combined? Nope, because the radicands are not the same, but the directions say to simplify, so you got to make sure that both of these guys are simplified. This one is not. Why is radical 12 not simplified? Because there's a perfect square factor of 4. That's right. So this can be split into radical 4 times radical 3. Radical 10, there's not a perfect square factor, so we really can't do much with that guy. So our final answer would be 2. Radical 3 plus radical 10. 2 radical 3 times radical 10. Please give me your answer as exact answers. In other words, I should see radical symbols. If you can't figure out how to type it in, just as always, just take a picture of your work, your pencil, paper work. Take a picture of it, insert that picture into the doc. You guys have been doing an amazing job showing your work, inserting that picture into the doc. It shows me that you know how to do this, and ultimately that's one of the main goals as a teacher, is to make sure your students know how to do it, and I need to see your work. Keep up the good work with showing that. But I don't want decimals tonight. I don't want decimals. I want your answers left as exact radicals. All right, let's do another multiplication problem. Let's take it a step further. Same directions. I think we're on example 4. I'm going to ask you to simplify, but this time let's do a quantity squared. Same directions, simplify. 4 radical 7 plus radical 5, this quantity squared. This should look kind of familiar. This is a square of a binomial. Remember doing this? We were actually in school when we first learned this. This is the square of a binomial. Most common mistake, kids try to square this and square this. Can't do that. You could do that if this was multiplication, but this is addition. This is a quantity squared. There's a special formula we used, but let's just kind of go old school with this. If you square something, what are you multiplying it by? You're not multiplying it by 2. If you square it, you're multiplying it by itself. That's right. So let's take 4 radical 7 plus radical 5 and multiply it by itself. So we have a binomial times itself. A binomial times a binomial. Now we're going to use a method that, again, we learned when we were back in school called FOIL. First, outer, inner, last. This is part of that payoff I was telling you guys. Because you worked so hard on FOIL a couple months ago, it should make this multiplication of radical expressions really pretty quick and honestly relatively easy. First, outer, inner, last. Okay, draw the arrow. So let's start with the F's. So I'm going to go 4 radical 7 times 4 radical 7. That would be 16. I'm going to kind of do it out longhand here. That's 16 times radical 49. So I multiplied 4 times 4. That's 16. Radical 7 times radical 7. That's radical 49, which happens to be a perfect square. So we're going to simplify that here in just a second. All right, let's do the O part. So I'm going to do the outside terms. 4 radical 7 times radical 5. What is that? That's right. It's 4 radical 35. All right, so far so good. Let's do the I part of FOIL. So radical 5, I'm kind of reading backwards, so I hope I'm saying the right thing. Radical 5 times 4 radical 7. That would be 4 radical 35 again. That's part of that special formula we looked at a couple months ago. All right, let's do the L part of FOIL. It's radical 5 times radical 5, so times itself. That's radical 25. What's kind of unique about radical 25? It's a perfect square. That's right. So a lot of this calculation you should be able to do mentally. If you want to use a calculator, that's fine, but try to do as much as you can mentally. So the first term here is really 16 times 7. That's right. Now these middle two terms, let me underline them here. These middle two, this kind of goes back to what we learned at the beginning of this video. This one and this one have the same radicand, so we would consider these like radicals. Let's add them together. If you had 4 radical 35, someone gives you 4 more radical 35s, how many do you have? You have 8. That's right. So this would be 8 radical 35. And then the last term is just the square root of 25. That's 5. All right, let's clean this up a little bit using PEMDAS. 16 times 7, that's 112. Plus 8 radical 35 plus 5. We are almost there. I think you can see that. Yep. And then the last thing we can do, we can add these two terms right here. They're just constants. So our final answer would be 117 plus 8 radical 35. That's a great problem right there. It's a good looking board. 117 plus 8 radical 35. Awesome. All right. We're getting close. We got 2 more problems left. Let's try one more FOIL problem. So we'll call this example, I think we're on 5. Let's simplify again. Let's go radical 6 minus 2 radical 3 times 4 radical 3 plus 3 radical 6. Just making sure I got the right problem down. Alright, this one we can just straight up start foiling it, right? Anytime you see a binomial times a binomial, you know FOIL's in your future. These cannot be combined. They're not the same radicand. Same with these two. Cannot be combined. Alright, let's start foiling this. Let's start with the F. So we have radical 6 times 4 radical 3. That'd be 4 radical 18. Then the O part of FOIL would be 3 radical 36. I'll show the board so you know what I've done so far. I've done the F and the O. Alright, time to move to the I part. So that would be what? Negative 8 times radical 9. And then the L part of FOIL would be negative 6 radical 18. Alright. Pause the video if you need to. Let's clean this up a little bit. I noticed right away that this first term and this last term are alike. That's right. They have the same radicands. So let's go ahead and combine these two together just to kind of clean this up. If you have 4 radical 18, take away 6 radical 18s. That's right. It's negative 2 radical 18. These two should be pretty quick because this is a perfect square and so is this one. So this is really 3 times 6. That's 18. And this other one is really negative 8 times 3. That's negative 24. So that's negative 2 radical 18 minus 6. Now if you left your answer like this, I cannot give you full credit. Everything we've done so far is correct, but how come I can't give you full credit for this? That's right, the radical 18 is not simplified. Always have to ask yourself, is there a perfect square factor? 9 is a perfect square factor, so I can split this one into negative 2 times radical 9 times radical 2, and then don't forget about your minus 6. So my final answer would be negative 2 times 3 radical 2 minus 6. So my final answer would be negative 6 radical 2 minus 6. It's kind of small, but I think you can see that at the bottom of the screen. Alright, so I'm going to go through this last one real quick because I just realized I only got about 5 minutes left of video space here. So I'm going to move through this last one kind of quick, but hang with me, and as always, email me if you have questions. Same directions. This one's a little bit of a curveball. Very last problem on your Google Doc is very similar to this one, so if you need to rewatch this video, go ahead and do so. So here's the problem. It's negative 2 all over radical 6 plus radical 11. This is pretty high on the funk factor, right? You just got a plain old number up here on the top, but then you have these two like crazy looking radicals down here on the bottom, which cannot be combined because they're not like radicals. So there's got to be kind of a way around this. How can you kind of skirt around this using the rules of algebra? And in order to divide this, you need to use what's called a conjugate. You'll see this again next year, but I wanted to introduce it to you here today. You're going to use what's called a conjugate. So let me give you like just a quick abbreviated definition here. Conjugates, they are the sum and difference a little messy, but I think you'll be able to read it here. The conjugates are the sum and difference of the same two terms. So kind of the formalized definition here. Conjugates are the sum and difference of the same two terms. What does that mean? You might be wondering, okay, I wrote the definition, but I still don't know what it means. So if you look at the bottom of our problem here, we have radical 6 plus radical 11. The conjugate of that is found by just switching this sign. So it's kind of like an opposite, kind of. So the conjugate would be radical 6 minus radical 11. So as the definition here says, same two terms, except instead of the sum of those two terms, we're taking the difference of those two terms. So in order to attack this problem, we have to have some understanding of how to find a conjugate. So to find the conjugate of this denominator, just switch the sign. And this next statement, I want you to put like a star next to it, because you're going to be using this on your Google Doc and definitely going to be using it next year. So to approach a problem like this one, you're going to multiply the top and the bottom of the fraction, so the numerator and the denominator. So put a star next to the statement if you could. So to attack a problem that looks like this, that has two unlike radicals in the bottom, here's kind of the trick, the shortcut, the math property that allows you to do this. You're going to multiply the top and the bottom of this fraction by the conjugate of this. Multiply the top and the bottom of this fraction by the conjugate of this. Pause the video if you need to, because I'm going to erase that. So let me go ahead and show you, put this into practice what I just said. I'm going to multiply the top and the bottom, so put two dots, multiply the top and the bottom by the conjugate of the bottom. So I change this plus to a minus, minus. Now, big question, I'm only going to give you like 10 seconds to kind of digest this. Why is this allowed? Why is this a thing? If you, and I think we talked about this here in the last couple weeks, if you multiply by a number, and this is just a number, it's a funky looking number, but a number over itself, I could put a fraction bar right there, a number divided by itself, you learn at a very young age. You take a number and you divide it by itself, what do you get? You get 1. If I multiply by 1 over 1, I'm not changing the value. I'm changing the look, but I'm not changing the value. It kind of goes back to the wedding cake from the beginning of the year. I can multiply this by 1, multiply this by 1, change the look, but not the value. So let's do that. Let's multiply. So we have a number times a binomial. So this one I'm going to distribute the negative 2. Let's do that. So this top is going to be negative 2 radical 6 plus 2 radical 11. So I just distributed the negative 2 here, negative 2 radical 6. A negative times a negative, that's why I got a positive here. This is positive 2 radical 11. Can I combine these two together? Not a chance, right? Because they're not like radicals. The bottom, it's a little bit more work. I have a binomial times a binomial. So what do you have to use? That's right, you got to FOIL this one. But the good news is, well, let me back up. The bad news is you got to FOIL. The good news is most everything here kind of cancels or becomes a really easy calculation. All right, so let's do this. Let's use FOIL. So radical 6 times radical 6. That's radical 36. That's going to be easy to simplify here in just a second. Let's do the O part of FOIL. Radical 6 times negative radical 11. That's negative radical 66. All right, let's do the I part. Radical 11 times radical 6. That's positive radical 66. Oh my stars. Good gravy. Those cancel. That's kind of nice. And let's do the L part. Radical 11 times negative radical 11. That's going to be negative radical 121, which, oh my stars, that's a perfect square. As ugly as this denominator looks, these two cancel. This one and this one, they're both perfect squares. So initially the bottom looked really tough, but it ends up simplifying really, really nicely. That happens most of the time when you use conjugates. Okay, so the top, it stays the same. There's really nothing we can do with those. It is completely simplified. But the bottom really simplifies. It's really 6 minus 11, which is negative 5. And that, class, is as far as you can go. There's really nothing else we can do. This is completely simplified, and the only way we were able to get that is by using conjugates. Definitely something you're going to see next year. Wanted to introduce it to you today here on the video, and again, you're definitely going to see that on your Google Doc. Keep up the great work. We are almost there. You know, you can really start to kind of see that glimmer of light at the end of the tunnel, and we're almost there. Your hard work is paying off, and I really, really appreciate it. So, as always, appreciate your time on this video. Be kind to one another as we get into the weekend here. Be kind every day, but especially over the weekend. Be patient with one another. It really goes a long way, and above all else, please make sure you continue to pray. Pray for each other, pray for your classmates, our school, your family, your friends. Pray for the world, all those first responders, that they continue to be safe, and God's healing touch be on all of those that are impacted during this unusual time. So appreciate all you've done, and if you have questions, shoot me an email. Keep up the great work. Have a great day.